Hello everyone and welcome to today's webinar on optimizing ventilation system design. It's a pleasure to have you all here. My name is David. I'm going to introduce myself in a second a bit more in detail, but let's first get some technical details out of the way. We're using this GoToWebinar tool to broadcast this webinar today, and to make sure that the sound setup on my end is okay, I would ask you to quickly raise your hand. There's a little option in GoToWebinar where you can raise your hand, and that gives me the feedback that you can hear me clear. Yeah, all right. I can see first hands going up. Fantastic. That's great. I apologize a lot for the medium quality sound today because we just moved offices with SimScale and we haven't set up our audio room yet. So there's a little bit of an echo behind me, so I'm sorry for that. We're going to fix that soon and going to have better audio for the next webinar. All right, a last technical note. In GoToWebinar, it's possible that you can ask questions. So this webinar today will roughly go 25 to 30 minutes, and we're going to have some time by the end of the webinar to address some questions. So as we go through the webinar, just ask your questions, type them in there, and by the end of the session today, I'll try to cover most of them to address them immediately. If a question remains unanswered, you have my email address, so feel free to drop me a line there, and I'll take care of your question then. All right, without further ado, let's dig into this today. A couple of words what you can expect of this session. So what will not, let's start with what this is not about. Unfortunately, this session won't be about the details of flow simulation, the details of the finite volume method or turbulence modeling. Today it's really about more on a top level, how CFD, how flow simulation in general can help engineers, designers being involved in some sort of design of ventilation systems to get their job done faster, to get it done better, to build a better product faster with the help of simulation. And so we're going to look at a very, very high level on how CFD transforms the design process, as well as look at one real-world example how CFD is leveraged, and that you get an idea how CFD can be used to design better ventilation systems faster. Let's start from the very beginning. So you're carving out 30 minutes out of your schedule today to listen to this talk, and so the question is why, right? Why should I care about flow simulation at all? And I often use this little illustration to give a feeling for why simulation and flow simulation in particular is time well spent in a design process, or as a designer or as an engineer. And at the bottom axis here, you can see the design process timeline. At the y-axis, you can see sort of a qualitative measure for the cost your product will have, as well as its performance, right? So sort of a mixed axis there. And if you think your design process through, what you're actually doing is you're defining the performance and the cost of your product by the biggest amount of it is defined very early, right? In early design phases where you're starting to explore the design space, talk about conceptual design, etc., this is where most of the most impactful decisions are being made when designing a product. And interestingly, this is not just the case for ventilation systems, right? We have customers in the architecture space where it's the exact same thing, right? The costs of a building are designed at the very beginning of the design phase. And so for every physical product designers and engineers conceptualize, the biggest impact is being done at the beginning, or is being made. While sort of asymmetrically to that, the realization of that cost, so when you actually start spending money on that product, or when you're actually seeing if this performance will facilitate in the field, it's sort of much slower, right? Specifically when we think about cost, initially having engineers sitting in front of the computer is much cheaper than field testing and prototyping and that sort of stuff and first prototype iterations, etc. So the cost actually is facilitated at a later point in time. And so ultimately, coming back to bringing this point home, why you would care about simulation is this is the region where design decisions matter the most, right, or have the biggest impact. So in simulation and flow simulation in general allows you fundamentally to make better design decisions earlier, and therefore increase the chances of having your design process result in a design that's actually fit for purpose, that's production ready, that will set you apart from your competition. And so better can have in different sort of industry verticals in different companies, better can have a different meaning. So sometimes it's about lowering cost of a product, sometimes it's about lowering energy consumption, keeping deadlines, lower failure risk, etc. At the same time, different people in a company will see better in different ways. So the designer has a different opinion than the engineers, has a different angle of view angle than the manager. And so today, when we talk about ventilation systems and more specifically about an air intake system that we're going to look at, it will really be about lowering pressure drop. And why? We're also going to talk about that in a second, but a better design decision or a better design in today's session will be really what can we do given certain constraints, what can we do to lower pressure drop? We're going to get there in a second, but that's just very sort of the very big picture why simulation is a helpful tool in a design process. So then, okay, that was simulation and now SimScale, right? So why should you care about SimScale? And I mean, there's a ton of simulation tools out there, right? There's a ton of flow simulation tools out there. So why did we decide to develop another one, to develop a new one from scratch? And the reason is that we think tools out there, the existing tools out there, have three main barriers that keep a lot of designers and engineers from using it. And the first one is we want it to be flow simulation accessible. This means no hardware deploy, no hardware purchasing, no hardware maintenance of that very expensive and hard to maintain high performance computing hardware. We wanted it to be instantly accessible, right? And so we put it in a web browser. So SimScale runs entirely on the cloud. A web browser is everything you need to start using SimScale. The next thing was we wanted to lower the financial barrier, meaning that it shouldn't break the bank if you want to start using simulation or if you want to explore whether or not simulation is a tool that's helpful for your design process. So we wanted it to have a significantly lower initial financial commitment than what's available on the market. And so today, SimScale actually comes with a free plan, so you can use it right away entirely for free. If you are ready to publish your projects, right? So basically all of the projects you can do in the free plan will be publicly available, and so these public projects become very helpful for other engineers, right? And so it's sort of this community aspect behind SimScale. At the same time, the paid plans start at a significantly lower threshold than other software tools, and so depending on the needs of the customer, we put together a custom plan. And last but not least, for everyone, that's sort of our tagline, that you should be able to use simulation without a ton of academic background, without a ton of training, but more sort of community enabled. That's our view here. So we've meanwhile gathered tens of thousands of public library projects that you can use to start your simulation projects from. So you don't have to always start from scratch or learn it yourself. There's lots of simulation content out there that you can use. There's a lot of training content that we have that's meant for consumption by yourself, these sorts of things. And at the same time, we do take advantage of the cloud-based nature of SimScale. So we have a live support chat. You can get directly access to our support team via a convenient chat functionality, and you can share your projects with them. They can directly look at it, these sorts of things that are only possible in the cloud. And with that, we want to truly democratize simulation so that simulation can be used in projects and companies where it was not economically feasible before. That's kind of the tagline, or the bottom line. And don't take my word for it. I want to sort of show you what this exactly means and make this a bit more hands-on in a second. To get a big picture overview of SimScale, it's not just, so today we're going to talk about aerodynamics, right? The air intake systems that we're going to take a look at, or a closer look at, will be about incompressible flow simulation. So we have air going through and we're interested in reducing pressure drop. But SimScale is a general purpose simulation environment. So we've got structural mechanics, FEA, nonlinear, linear contacts, assemblies, parts, etc. As a module, we've got flow simulation, and also there, today we're going to look at single-phase incompressible, but we're also doing compressible, multi-phase, heat transfer, conjugate heat transfer, these sort of things. And then thermal, we've got both conduction, convection, radiation, then a couple of more exotic physics, such as here, particle phenomena, so bulk flow simulations, bulk material simulations. So bottom line, it's not just CFD, what we're going to look at today. Every customer gets access to the full range of physics. I touched a little bit on this. We're going to take a look at this later. So, that number is meanwhile outdated. So we have tens of thousands of projects being added to SimScale on a monthly basis. And so there's lots and lots of simulation content that you can leverage for your own purposes. You can just like explore them. All of them are publicly available, and make copies of it and use it for your own purpose. Before we move on, let me see if there's any urgent questions popping up or any technical issues. That looks okay. So let's continue at that point. So that as a little introduction to flow simulation, why you should care about flow simulation, why you should care about SimScale, what makes us unique. And so let's dig deeper into the topic of today. When we talk about ventilation systems, there's all kinds of ventilation systems, right, in different industries, where it's about moving air to under certain constraints, under certain performance criteria that you need to meet, under certain norms or legal constraints that you need to meet, etc. And today, as an example, we want to look at an air intake system. So basically, this is in the power plant industry. So this is a system where you can see in green. So basically, from the yellow part on the right, air is being sucked in through the air intake system in green, and then basically move to the blue part and then to the exhaust stack. And there's all sorts of components in here, and we won't talk in detail. Also, we won't talk in detail about gas turbines and power plants, etc. today. We really want to focus on this air intake system, the green part, in a second. So this guy. And another illustration is here on the right of this, and this comes very close to the application that we'll simulate today. So this has the task of bringing air from the outside and serving it to the gas turbine, to the compressor part of the gas turbine. And so there's all sorts of functional components within this air intake system, right? First, we can see the weather hood. So sometimes there's even bird shields and that sort of stuff, so to make sure that you're only getting air in and not other stuff that might be around this air intake system, depending on where you install it. Afterwards, depending on the exact application you're looking at, you could have a filter section, so and different kinds of filters, so for very coarse material and then for very fine particles. And also we're going to touch on that later in the simulation a bit. But here we can also already see the filters and how the air is moving through. And a transition part, so we're going to change cross sections to make it to have it to dock it to the gas turbine, the turbine's cross section, and then silencers. Oftentimes also constraints our customers face to make sure that the noise level is on an acceptable level. And then last but not least, sort of you want to change the direction of the fluid to serve it or to bring it to the gas turbine or to whatever component this air will consume. And before we go on and dig deeper into this, we've got customers that are leveraging SimScale for many different kinds of such ventilation systems. So it might be in the air conditioning sector, so heating, ventilation, air conditioning, where people are also concerned about pressure drop, but oftentimes also about thermal comfort, these sorts of things. We've got people in wind engineering, right, where oftentimes other constraints are being faced by engineers dealing with ventilation systems. So while today we're really going to take a look at such a power plant air intake system, the methods and the things, most of the things I'm going to touch today will equally apply to other industries. And we thought that's a very good example to visualize these aspects. All right, and so just getting back, on the left you can already see the design we're going to deal with in a second. So you can see this is sort of the negatives of the flow channel that we modeled here that comes close to this air intake system. So we can see from the left there's the weather hood, and then we're going to go through a first filter, basically a pre-filter section. There will be another filter section that we're going to model in the simulation, and then there's the silencers. And we have the change of direction, and then we serve the air to the gas turbine inlet, to the compressor part. And that's the design we're going to simulate today and going to take a closer look at. But before we move on, I found a very interesting, or a colleague of mine found a very interesting paper that deals also not with that air intake system, but with another one that you can see in the sources at the bottom. And there was a little sort of back of the envelope calculation on how important or how much leverage this an optimization or an improvement of such an air intake system design can have for the entire operation of the entire gas turbine. And in that paper, they looked at a specific gas turbine of that type and of that power. And what I found very, very interesting is that basically there was a little calculation saying if you reduce the pressure loss, the pressure drop across that air intake, by 250 pascals total pressure drop across that air intake, you're going to improve or increase the power output of the entire gas turbine by 0.36%, right? Which sort of doesn't seem to be a lot, honestly, right? I mean, I'm not shocked by that number. But overall, if you continue that calculation, that gives you a total gain of this. And if we assume this operator makes 0.1 dollars per kilowatt hour, we're going to end up over the year with a huge amount of additional revenue you can make with that gas turbine, right? And I guess without now sort of drilling down in all of these numbers and exactly digging into it, I think it just gives an idea of how pressure drop of such a component in the ventilation system basically has a huge impact on the bottom line. So I found that very interesting, and sort of using that as a motivation, and let's dig into it and sort of improve the pressure drop, right? So that's what we're going to look at. We saw it already: weather hood, filter section, transition, silencer, and then we're going to move it down here. And what we're going to do, and I won't be able, because it's supposed to be a very short webinar, so we only have half an hour. I won't show that in detail, but what we're going to do, just to give you the feeling for such a simulation process with SimScale, is we're going to bring in that CAD model into SimScale. We're going to generate a computational grid for that model, and then we're going to set up a simulation for it. And I'll just briefly touch on each of these steps, because you can basically, this very project I'm going to create today, or we're going to look at today, is publicly available on SimScale. And so you can just go in there yourself. Everybody, you don't even need a SimScale account. You can just go to simscale.com/projects, search for ventilation system, and this project will show up, and you can take a closer look yourself at it. All right, so much for the theory. Let's quickly get a feeling for how SimScale works. Let me quickly log out to really show you from the beginning how this works. So some of you might already have a SimScale account, some of you might not. So just to get the full picture, SimScale is entirely cloud-based. It runs in a web browser. So you simply go to simscale.com. If you do not have an account yet, you can create one. It costs you a minute. There's a free plan available, so there's no charges if you want to just explore. And once you have an account, you can log in. So I'm logging in. American keyboard, sorry for that. And then that brings you to your dashboard. Here's the public projects I talked about. So you can find here tons of different projects showcasing how SimScale can be used, tens of thousands of them. There's a very active forum, etc. But that's not what this webinar today is about. So what we're going to do is we're going to create a new project and say, okay, air intake, airflow, flow simulation. As I said, when you're a paid customer, you can create private projects. As a free customer, you can only do public. So we're going to keep that private, and I'm going to bring in the model, the CAD model of the initial, of the base design, I call it. All right, so the new project is created, our CAD model is imported, and so we can just jump into it. And wait, was that now the right project? Let me quickly check. Basically, you can bring in your CAD model like this and then start generating a computational grid for it, right? The good part is zero install, zero software footprint, hardware footprint on your end. There's nothing you need to do. It's just your web browser, right? And then from here, I would generate the grid, set up the physics, etc. But as we only have a couple of minutes left, I just want to walk you through the completed project and show you how you would basically run such a project on SimScale. So that's the one that is publicly available. You can just search it under public projects. And so to give you a feeling for what it means to set up a simulation on SimScale, this is the base geometry I uploaded, right? And so as a first step, what you do on SimScale is you create a computational mesh. So you basically discretize your CAD model into small pieces, into small cells, and that allows you then to use simulation methods to predict the physics in it, right? So here you can see lots of very fine cells. SimScale provides both automatic as well as parametric meshing technologies that you can use to create a computational grid. I switch over to the simulation designer, and basically here I just want to walk you through once to showcase what it means to specify physics on SimScale, right? So here you can see that as a customer you get access to all simulation types, flow, solid mechanics, thermal, everything's there. And once you've chosen an analysis type, afterwards this tree is populated with options, and it shows you which one you need to set, so which one are mandatory, which one are optional, and which one you're already set. So green means already set, blue means optional, and there's nothing red, so I could run that one. And I want to walk you through once, so just the most important things. So first I specified a material, right? In that case it's air, so I specified air as a material, and then the rest, the initial conditions, I left them as is, and then basically I just set up 3 boundary conditions, which essentially means how does your system behave at the ends of the computational domain, so at the boundaries of what you want to simulate. And so the first one is a pressure inlet. Let's see where we applied this one. Switching here. So we can see that obviously here is where the air comes in, right? You can see the red ones. So there's the weather hood. And so we said that the gauge pressure here is 0, right? Which makes sense because we have atmospheric conditions down here, out here. And so we want this to be gauge pressure 0. The other important one is that guy over here. This is the outlet, right? And we drive that with a fixed velocity. Oftentimes I see customers using a mass flow being assigned here, or a volume flow. All of that's possible. And the and in that case, we just said, okay, a fixed velocity of 6 meters per second into X direction, right? That's sort of, I'm fixing the amount of air that's being served to the gas turbine here. Last but not least, physical walls. So all of this is defined as walls, right? And then, I mean, that's essentially it. One thing I wanted to highlight is that you have access to large computing power. So in that case, we ran that simulation for 32 on a 32-core machine, and it took, I think, roughly 90 minutes, roughly 90 minutes. Yeah. And so you can leverage the compute resources of the cloud. So bottom line here is you bring up in your CAD model. It's SimScale acts CAD neutral. So we've got customers with all types of CAD systems. You bring in your CAD model, you create a mesh, you set up the physics, you run the simulation in the cloud. And to not invest too much time on the how you do that, let's look at why we should do that, or so what's in it for me as a designer, right, if I run that simulation. So let's continue here. Once your simulation ran through, you can post-process the simulation results. So that means you can visualize the fields that you simulated. In that case, it's an incompressible flow simulation. So we can afterwards visualize pressure, velocities, and turbulent quantities. In that case, we're mostly interested in velocity and pressure, right? And so this is I'm sorry, I skipped that one. This is a screen cast of analyzing. Let me see what's going on now. One second. I'm sorry for the bump here. Let me see. There you go. This is now a screencast of how I'm interacting with the velocity field of what I simulated here. So this is a streamlined visualization of the velocity. So blue, everything that's blue is under 3 meters per second, right? So very low velocity. And we can already see here that behind the silencer, we have these two vortex structures being formed in the corner of the duct, or of the air intake system. Same happens after this after this 90-degree turn, and then on both ends or outlets of the system, we can see these huge vortices being formed, and a backflow sort of recirculation area appears. And this sort of now fine-grained access to how does the flow look like, how does the flow field look like, allows me as a designer or engineer now to make design decisions how I could improve that, right? And to dig deeper here, that's a static visualization. So we can see that all of these blue areas in the duct part after the silencer basically means here vortices are formed, the effective cross-section for the flow is being reduced, energy is being wasted, right? So I'm losing energy here, I'm losing pressure, the pressure drop increases, right? So what I want to do is I want to mitigate these recirculation areas, and that's sort of what we're going to do now. To dig deeper, so these are the recirculation areas I want to focus on and mitigate them. Here, that's in the top right, you can see it's a mid cross-section through the entire flow channel, right? And on the left, we can see this is velocity being plotted on a scale from 3 to 25 meters per second. And here it gets very clear, right? I have the blue part at the top here. I have the blue part down here. This is what I want to mitigate. Rescaling this to 10 meters per second max velocity even shows it clearly, right? I'm blocking half of the flow cross section here at the outlet. It's another visualization of the velocity field. So my turbine is being served within a very inhomogeneous flow field, right? And the pressure field helps me to see where I'm losing pressure, right? And obviously I'm losing here in the beginning through the filter parts. I'm losing then via the cross-section change here. I'm losing a lot via the silencers. And the interesting part that I want to take care of now is the losses that I'm seeing here, right? At the at the 90-degree change of direction. And so to drive that point home, what we're going to do is we're going to simply make very simple design changes, right? In a first step, we're going to introduce some guiding vanes, so simply some sheet metal in the flow channel here at the top. And in a third iteration, we're going to introduce a radius at these corners. And running these simulations with SimScale again in the same manner allows me to sort of compare what's happening. Here again, I'm looking at gauge pressure. And this was the initial design, right, that we looked at. And already now I can see that. Can you see the difference? I think I highlighted them. No, unfortunately I didn't highlight them. I can see that this blue part here, right, is already significantly smaller over here, right, and even more homogeneous here, right. So that's exactly what I want, right. In a second step, that stuff here, right, I can see that this looks already more homogeneous. What I want, right? It's exactly what I want to introduce, right? Less pressure drop across the entire air intake. And then let's move on. Oh, I need to clear this. Sorry about that. Rescaling the gauge pressure makes that even clearer, right? So I can see that from blue to red, from red to blue, here on the left, I'm losing, this is my baseline design, I'm losing quite some pressure. And so with the same color scale, I can see that the outlet here in the design 2 has a higher pressure, right? While the design 3 has an even higher gauge pressure, right? So I'm losing less pressure. That's a qualitative understanding of how these improvements are made, right? And the most significant ones are here between 2 and 3. So I can see that still there's quite some pressure lost, and this is gone over here, right? Which is exactly what I want as a designer. Moving on here, and this is the velocity field. Also here, I can see the recirculation areas are smaller. I could mitigate them effectively with these changes. So these were all a qualitative understanding of how my design changes impacted the flow field. And you can also do that quantitatively, right? So here we plotted on the left the gauge, the pressure drop, basically the pressure drop, the absolute pressure drop across the entire air intake system, and averaged over the outlet, right? So pressure, average inlet, pressure, average outlet. And we can see that from the baseline design to the design 3, I could reduce it by a little bit more than 80 pascals, so 16%. And coming back to the initial line of thought, right? There we knew that 250 pascals was a huge difference to the bottom line of the operator of the gas turbine. And so in that case, it's 80 pascals. So a significant improvement. So to drive that point home, this was basically my design 1 right here on the left, my design 3. And what I introduced is 2 very simple design changes, right? And I could immediately sort of check on how effective are these design changes, right? Because sometimes, honestly, we've seen it. Sometimes you run the simulation and you can see, okay, I could now optimize this design, but the bottom line of it is so small, or the improvement is so small that it doesn't, I don't know, outweigh the manufacturing costs or something like that, right? So it gives you confidence as to which design changes make sense and which not, which have a huge impact and which have not. And so I invested very limited amount of time of my manual time. I invested computing time 5 hours because everything runs in the cloud. You can parallelize it, right? You can run all of these simulations in parallel on lots of cores. So overall, it was, oh, sorry, that's a typo, 180 core hours that I invested here in this entire simulation project. And I could come to a more homogeneous flow, outlet flow to the gas turbine. We talked about it, 80 pascals reduction of the pressure drop, which equals a 16% relative improvement of the pressure drop to the initial baseline design. And yeah, I can simply, as an engineer and designer, I can make my design decisions with a higher confidence. That being said, let me just, if you have not yet created a SimScale, an account on SimScale, this is how you get started. It's as simple as that. And with that, I want to say thanks a lot for the attention today. I appreciate it. And If you have any specific questions about what we talked today, or a follow-up question where you can or you can't find the project I talked about, let me know. I'm happy to get in touch. We have an applications engineering team here with lots of CFD engineers that might be able to assist you as well. And with that, I am unfortunately running out of time, and we'll leave you with that. Thanks a lot. Have a good one. Take care. Bye.